In this lesson, we'll discuss the different types of drainage systems, which relates to our terminology objective.
We'll start with discussing the types of drainage systems, and there's really three main types that we're going to talk about, starting with surface drainage. Surface drainage is the diversion or orderly removal of excess water from the surface of land by means of improved channels or ditches, supplemented when necessary by shaping or grading of land surfaces. Surface drainage is the easiest and least expensive way to improve the land drainage. The most obvious type of surface drainage is doing land shaping to create ditches, like I'm showing in this picture, this illustration, but swales and grass waterways are also examples of improved surface drainage. It's usually pretty easy to pick out a ditch from a stream because drainage ditches tend to be straight, streams tend to not be straight, and farmers or drainage districts usually maintain ditches by cleaning the sides, so you might see some scraped ditches with no vegetation, and that's not great for erosion, but drainage districts are charged with maintaining the drainage capacity, and so they try to keep those channels orderly. One nuance that we have here is that we have a lot of ditches around here in east central Illinois, but I wouldn't consider these ditches really surface drainage ditches. They're really more just part of the conveyance system to move tile drainage water downstream. So the picture on the top, I would say that would be a surface drainage ditch. The picture on the bottom is more of a conveyance ditch rather than actually surface drainage in itself. So even though surface drainage methods like ditching are usually the cheapest option, this kind of drainage doesn't always solve the drainage issue. For example, if you have a perched water table like we have here in Illinois, surface drainage won't solve that for you, and so in that case you need subsurface drainage, which is the diversion or orderly removal of excess subsurface water from the soil using a conduit. So where we have a tight clay layer which creates an impermeable boundary that prevents water from moving downward in the soil. For us, at about 3 or 4 feet down, we have this tight layer that prevents water from moving downward. In that case, we would want a subsurface drainage rather than a surface drainage system, which wouldn't address the issue. So, what is a tile drain? I keep saying subsurface drainage. What's a tile drain? Tile drainage is actually a very specific definition, and you can see that from the ASABE standard terminology document. A tile drain is technically something very specific. Tile drain is a drain constructed by laying drain tile, like shown in the picture, with unsealed joints in the bottom of a trench, and then you refill over that. Tile is usually constructed of clay, like shown, or concrete. This raises an important terminology issue for us. We colloquially or informally or kind of with jargony, we refer to the kind of drainage that we do here in Illinois as tile drainage. But scientifically, we should call it artificial subsurface drainage. We shouldn't call it tile drainage, especially for our new drainage systems that have gone in the last 20, 30, 40 years. We should call it artificial subsurface drainage if we want to be technically correct. So I switch back and forth between saying tile drainage and subsurface drainage a lot, but when I write scientific journal articles, I make an effort to always use the technically correct term, which is subsurface drainage or artificial subsurface drainage, rather than the informal jargony type term of tile drainage. But you'll notice I do switch back and forth when I'm just talking about this practice of subsurface drainage. Moving on, one of my favorite subsurface drainage systems to talk about is called mole drainage. And here's the global learning objective, because mole drainage is the kind of drainage that's often used in the United Kingdom, in Ireland, and in, for example, dairy pastures in New Zealand. Mole drainage is man-made, unlined, circular channels made in the soil. It has to be a very heavy clay soil that has low hydraulic conductivity. Like I said, mole drainage is done on tight, heavy, clayey soils because it's essential that the soil is able to be formed into an unlined channel. There is no pipe in this kind of drainage system unless it's a mole and tile drainage system like shown in this picture, where the mole channel, which is unlined, connects to a tile system at the edge of the field. The idea though for the moles is that you pull a foot implement through the soil like I'm showing here, and it literally forms a channel in the soil. And because the soil is very typically clay soil, heavy clay, that channel will stay in place. The advantage of mole drainage is that they're cheap, and so that they can be installed with relatively close spacing and relatively shallow in the soil. So they're typically 1 to 4 meters apart and usually about 1 foot deep, which is much shallower than our tile systems here. We'll talk about that in another couple lessons. The downside with mole drains is that they don't last forever, and you typically have to redo them every couple of years. Remember, there's no pipe that you're putting in. It's just a channel that you're forming with this little foot implement in the soil. And again, you have to have the right soil type to do this. The last kind of drainage system that I'm going to talk about, remember I said there's 3: surface drainage, subsurface drainage, and then the third one is irrigation and drainage. And this one is interesting because it's a combination of irrigation and drainage, which might not make sense at first, but this is actually one of the most common types of drainage system globally. Drainage systems in arid climates are typically this irrigation and drainage combined system rather than just a drainage system like we have here in the humid Midwest. So the idea with irrigation and drainage is that plants uptake essentially pure water from the soil, which leaves salts behind. You might be thinking, well, there's no salt in fresh water, it's pure, but think back to when we talked about the National Atmospheric Deposition Program, and we looked at some NADP data online. Even rainwater has salts in it. It has chloride in it, it has some nitrate in it, so even rainwater isn't technically pure. And the same is true with irrigation water. Even if it's groundwater, water is rarely super pure. It's always going to have some salts in it. So when you're irrigating, adding that supplemental irrigation to your plants, the plants essentially take up pure water, which leaves the salts behind, and this issues of salts becomes exacerbated when you're irrigating. The salts, especially in an irrigated system, have to be leached out of the root zone so that they don't accumulate. This means that when we irrigate, we typically apply what's called a leaching requirement. We apply more water than is exactly needed by the plants. And this leaching requirement that you add on in addition to the water that's required just for the plants, that leaching requirement leaches those salts out of the root zone. But as you leach those salts downward, you are at risk of raising the water table because you've added more water than the plants actually need. And so in many areas, you have to remove that additional water to avoid raising the water table, hence you need a drainage system. There's not many drainage systems in Kansas or Nebraska where they do a lot of irrigation because that drainage is naturally provided. They don't need to provide any additional drainage even though they're irrigating. Out west, however, these drainage systems out here that you see popping up, those will be typically irrigation and drainage systems. The climates will be much more arid, and so that's an indication that you're going to have an irrigation and drainage system if you're talking about drainage in that part of the country. Next, I want to talk about patterns of subsurface drainage installation. We're going to start with a random pattern. This is the oldest kind of drainage system we have around the Midwest. Random tiling or random style of subsurface drainage removes water from localized depressions. So it's suitable for rolling land with really isolated wet spots. This is sometimes used to drain grass waterways or other localized wet spots as illustrated here. This is inexpensive because the drain lines follow natural depressions and draws. The laterals are not parallel, but rather placed according to the size of the wet spot. The next kind of drainage is a parallel design, and a parallel design is much like what you would think. The lines are all installed in a parallel fashion. This is used for when the entire field is poorly drained and the need to improve the drainage is less localized. So a lot of our drainage systems that go in today are this parallel type pattern tiling. This is used for flat and relatively uniform fields that are regular shaped. The laterals are perpendicular, or in other words, at 90 degrees to the main. So what do I mean when I say main and lateral? The main is the primary conduit that receives water from smaller conduits. The main is often connected to the outlet, or the main is the outlet. So you see the outlet here. And then the laterals are the secondary or side channel ditches or conduits. So the laterals are what connect to the main. Think of it like a tree. The branches are the laterals. If you have submains, those are larger branches that lead to the main, and then the main is the trunk of the tree. You can think about a parallel drainage system with a tree analogy there. And then the outlet is the point of discharge from a stream, a river, a lake, or an artificial drain. So we talk about the outlet of the drainage system a lot. This is just typically where the pipe daylights into a stream. For parallel drainage systems like I'm showing here, cost usually becomes limiting. You want to, folks often want to do close spacings, space the tiles space the laterals as intensively as they can. But that also causes increased cost. So cost is kind of a balancing point for parallel drainage systems. And then lastly, I'm showing another variation of the parallel drainage system. This is a herringbone parallel system. And in this variation, the laterals are placed at an angle to the main, an angle that is not 90 degrees. With that, thanks a lot.